So good morning to you all.
Good morning, sir.
Yeah, good morning. So we were solving a couple of the problems on the CS strength, core pressure, and stress part. So in the previous class, we left in between one problem. So where we attempted up to point number D, I guess. So the drainage valve is opened and the soil allowed to consolidate under all pressure. What are the sigma U and sigma dash values? So this point number D we attempted. And next go to the point number E. So here it says comment on the nature of change in water content and degree of saturation of the.
No, sir. Up
Yeah,
to C we have completed, sir.
up to C.
Yes, sir. Wall is closed and it is increased to 320 kilopascal. That one, sir.
Okay, okay, no problem. So now we can stay. C are the others. Please confirm.
I think D was done, sir. The valve was
Yes,
open
sir.
and U was zero.
D
I
was
think
done
D was
already.
done.
Anyhow, I will repeat it. See, in case of the D, the drainage valve was opened. So when I say the drainage valve was opened, so D. So valve is opened. So what is the meaning of this valve is opened? So when you allow the consolidation by opening the valve, so there is no development of the pore water pressure. So your simple U component becomes zero. So that is the fundamental meaning of valve is opened, the soil is consolidated. So otherwise also you have to understand that when the soil is getting consolidated, meaning thereby you are allowing the water to go out from the soil sample. So when U is 0, so whatever remaining is either sigma 1 or sigma 3. Whatever there exists here, your sigma is remain as it is. So that is 320 kPa. And in fact sigma dash also same thing. So when U is 0, so your sigma dash will become sigma. So this is general condition. Okay, so there is a development of the pore water pressure only when the valve is closed. Now in E we can see such condition. So in D, where valve is open, so therefore we understood that there was no development of the pore water pressure, therefore U is 0. Now in the E condition, so up to D there was some amount of the consolidation that took place. So as a result, so there should be some change in the water content in the soil sample. Okay, so therefore the answer to the point number E is what is happening to the water content and what is happening to the degree of saturation. Since since the soil is allowed to consolidate, so up to point number D, so therefore definitely there will be some change in the water content. However, so the degree of saturation remain 100%. So this is possible. Okay, if you look at the fundamental definition of the water content and the degree of saturation, then you can able to understand. Suppose if you take the water content definition, it is the weight ratio, weight of water upon weight of the soil. So it is a ratio between the solid weight of the soil with respect to weight of water. But suppose if you take the degree of saturation, it is defined as the volume of the water in the volume of the voids. Okay, so the degree of saturation, the SR can remain 100%, even if the water content cannot be 100%. Even at water content of 50%, the sample can be fully saturated. Because there, for degree of saturation, you need to look into how much volume of the voids as occupied with the volume of water. That's what is the meaning of degree of saturation. So therefore, do not try to correlate bit by bit the fundamental definition between the water content and degree of saturation. One is weight relationship, another is a volume relationship. Okay, so this is the answer to the point number E. Next, point number F. So here, the drainage valve was closed. Now, you should immediately think that when the drainage valve is closed, there is a development of the pore water pressure. So that means now you are increasing the pore water pressure. Now what happened? They have closed the drainage valve and an additional axial stress was applied with the cell pressure held constant. So the cell pressure remained constant, but they increased the deviated stress to 100 kilopascals. Now since the valve is closed, as a result of the valve closed, now there is a build-up of the pore water pressure. So when you have reached the deviated stress of 100 kilopascals, the pore water pressure was increased to 80 kilopascals. That was the statement of the sum. So now if the pore water pressure was rose to 80 kilopascals, so then you are asked to calculate the pore pressure parameter. Now here, two things that you need to understand. If sigma 3 is constant, so which parameter between A and B got impacted? A or B?
A, sir.
No, sigma 3, cell pressure.
Which
Sir,
one
can
will
you
be?
please repeat your question?
See here, sigma 3 is constant and deviated stress is increased. As a result of increase of the deviated stress, there was a development of the pore water pressure. Now, is the development of the deviated stress and its consequent development of the pore water pressure is linked to which pore water parameter?
It is A bar actually.
A
A.
bar, sir.
A bar. Okay. So since sigma 3 is constant, so there will not be any change in the B parameter. B parameter. So this is what you need to understand. So since now you understood that there is only change in the A parameter, so you can able to calculate only the A. So how do you define the A? So delta UD, that is change in pore water pressure, divided by the applied sigma 1 minus sigma 3. Sigma 1 minus sigma 3. See, try to understand. There are two stresses that you are playing, sigma 3 and deviated stress. So what is the resultant change in the pore water pressure as a result of change of deviated stress as well as the change in the cell pressure. Here, so although you rose the deviated stress from 0 to 100 kilopascals, you did not change sigma 3. So therefore, effectively, the cell pressure is remained constant. Therefore, there should not be any change in the delta sigma 3. It should be 0. Okay. Now, only there is a change in the delta sigma 1. That is from 0 to 100 kilopascals. And as a result, the change in the pore water pressure is, see, at condition D, the pore water pressure is 0. From the 0, it is rose to 80 kilopascals. Therefore, the net change in the pore water pressure, that is delta UD, is 80 kilopascals. And net improvement in the delta sigma 1, that is deviated stress, is 100 kilopascals. Therefore, 80 by 100. So what you get is 0.8.
Sir, this 0.8 is A bar, na sir?
A bar and A, there is a small distinction. A bar normally we write when the sample is partially saturated. If the sample is fully saturated, then we use the A.
Yes, sir. In this case also A bar equal to AB. So if B is 1, then A bar equal to A. That's the case, I think.
Yeah, so no problem. No, but otherwise see. So in this case, fortunately, this is happening. Suppose, what if the degree of saturation is not 100%? In that case, it becomes a bar.
But in this case, B equal to not 1 because sigma 3 is 0. It tends to infinity.
Nothing to do with 1. See here, SR is 100%. In the point number E, it is clearly told your degree of saturation is 100%. So therefore, it has to be A only. Okay, so this is how you need to calculate the A parameter. Now, from the point E, what has been done? So at point number F, when the deviated stress increased to 100 kilopascals, there was no failure in the sample. Now, in order to fail the soil sample, what they have done? They have increased the deviated stress to 200 kilopascals. Increased the deviated stress to 200 kilopascals. Then the sample has failed. So at failure condition, you can rewrite the parameter A as AF into the final pore water pressure parameter divided by the resultant or improved the deviated stress. Okay. So there is a small distinction between this one and this one. A is a consequence of change in deviated stress. So you need to understand. But AF is also same, but at failure. So at failure, what was the total pore water pressure and what was the deviated stress? So here the deviated stress that was given as 200 kilopascals. At that condition, the sample has failed. Now here you can also see. So at failure, when an additional axial stress of 200 kilopascals had been applied, the sample failed, and at that stage, the pore pressure coefficient A was 1. So it is given. So AF was given as a 1. So then, what was sigma 1 dash? So what was net principal effective stress value at that condition? So, but for that, you need to calculate, because if you look at sigma 1 dash or sigma 3 dash, it is total minus effective. So total minus pore water pressure. So unless you determine the pore water pressure, so you can't able to determine the principal effective stresses. So based on the given data, we can able to arrive at sigma D is equal to 200 kilopascals and AF is equals to UF by sigma 1 minus sigma 3 into F. Now since AF is given as a unity, so I can take UF is equals to sigma 1 minus sigma 3 into F, which is nothing but the final deviated stress. So therefore, at failure condition, the pore water pressure is nothing but the applied the deviated stress. At failure condition or at failed condition or at the stage of failure, your net pore water pressure is nothing but the applied deviated stress. Okay, so that is only when you say AF is 1. But if it is not equals to 1, it is a different case. So once I know the UF, then I can able to calculate the sigma 1F and sigma 1 dash F. So initially a cell pressure of 320 kilopascals is applied. Now the sample has failed at a deviated stress of 200 kilopascals. So if you are asked to calculate sigma 1F, the net principal stress at failure condition, which is nothing but the cell pressure of 300 kilopascals plus deviated stress of 200 kilopascals. So therefore it is 520 kilopascals. So sigma 1 dash F is equal to sigma total minus pore water pressure. So total is 520 minus pore water pressure is 200 kilopascals. So therefore sigma 1 dash F is 320 kilopascals. Okay, so this is the answer to the point number G. Next, the last point. What was pi dash value if the soil had a C dash equals to 0? Now one thing is clear. So here C dash is 0, and you are asked to calculate the pi dash. So when I say C dash is 0 means your Mohr column failure envelope passes through the horizon, and where the angle made by the Mohr column failure envelope is pi dash. So suppose if I take some geometry, where I can show this geometry, because this is the most important that you need to understand. See, for example, this is the Moore circuit. So this is your failure plane, and this is the center of the circuit, and this is the pi dash value, and this is the geometry. Okay. So now this is, say, this is A, this is B, and this is C. So this is shear stress axis, and this is normal stress axis. Now A, B, C makes a triangle as per the geometry. Now here, if you look at the line BC is perpendicular to line AB. Usually, line BC is perpendicular to the line AB. Line BC is perpendicular to the line AB. Now, suppose if I draw the distance between A and C and B and C. So in terms of the normal stresses, can we able to write it? So what is the distance of AC?
Sigma 1 plus sigma 3 by 2.
Yeah, so sigma 1 plus sigma 3 by 2. Similarly, what about BC?
Sin
So
phi
this
dash.
is radius of the Moore circle. So sigma 1 minus sigma 3 by 2. This is all right? Okay, now take a geometry of ABC. ABC. Since this is a right angle triangle, so if I take sine pi, so this is, where is the hypotenuse and where is the opposite side?
AC and BC.
AC and BC. So this will be nothing but BC by AC. Is it correct?
Yes, sir.
Okay. So now I know the BC, sigma 1 minus sigma 3 by 2. I know AC, sigma 1 plus sigma 3 by 2. So can I write this as, so sigma 1 minus sigma 3 divided by sigma 1 plus sigma 3?
Yes, sir.
So either you can write in terms of the total stress or in terms of the effective stress. It is valid for both the stress conditions. So now here, let us look at it. From the point number G, I was able to calculate the sigma 1 dash F. So I know sigma 1 dash. Now what I don't know is sigma 3 dash. So calculate sigma 3 dash F. So cell pressure of 320, and at the failure, the pore water pressure is 200 kilopascals. So 320 minus 200, so this is 120 kilopascals. So therefore, I know now sigma 1 dash F 320 kilopascal, sigma 3 dash F 120 kilopascal. And based on this geometric derivation, sin pi dash is nothing but sigma 1 dash F minus sigma 3 dash F divided by sigma 1 dash F plus sigma 3 dash F. So you know the values of the sigma 1 dash and sigma 3 dash. So simply substitute in this equation and calculate the angle made by the failure plane.
The phi would be 27.03, I think.
I will be
27.03.
27.02. Okay. Just check it, others.
Sir, we can also do it analytically, na sir. Sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha from that.
But this itself is analytical only. Na?
Yeah, this is derived from the geometry. I mean, from that only the analytical relation comes, I think. Yeah.
Try means What is that equation you want to do it?
Sorry, sir.
Now here you are determining the pi, angle of internal friction.
Yes.
So which
The analytical relation which we have read, that is sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha.
yeah. That's also fine. But only suppose if you are unable. Yeah.
So if the failure plane doesn't pass through the origin, will this formula be still valid?
Yeah. This is still valid, but in that case, there is additional term comes into the picture. That's why I told you this derivation. For example, let us take. Okay. So let me rub up this one.
So by this also it is coming 27.04.
Yeah, it has to come both. Both derivations are from the same origin. Okay, so now since he is asking in another way, suppose if you take so this is what you are asking. So this is center of the circle, and this is nothing but your C component. Either you take C dash or pi dash, whatever it is. So now I will take, so this is A, B, C, D, E. And line DE is perpendicular to line ACD. Line AC. Suppose if the ordinate is, and again this is a pi, so it will not change. It will not change. So here suppose if this ordinate is C dash, what is this AB in terms of the C? Now I know.
C10 I.
So from here to here, this is sigma 1 plus sigma 3 by 2. And this is, so sigma 1 minus sigma 3 by 2. And what is this AB?
C dash cot phi.
C dash cos phi. That's it. So here, in addition to the sin phi, you will get one additional terms in terms of the cos phi.
Cot
So
phi.
C cos phi.
Cot.
The cot.
Uh,
The cot, sir, cot.
Cos only. C cos phi.
No, sir, cot. 10 inwards. Means 1 by 10.
Oh, C cot phi. Check it once.
Yes, sir, 1 by 10 is cot.
Okay. So then this is C part, whatever it is. Okay. So now here, suppose if I take this sin phi, same. So from the numerator of hypotenuse, the denominator will become two terms, sigma 1 plus sigma 3. So this summation of these two. Okay. So for a given soil, or if it is a granular soil where C dash is 0, you can directly use the sin pi dash is equal to sigma 1 minus sigma 3 by sigma 1 plus sigma 3. In case if it is a C5 soil, then you can still use the same the analogy, but where you need to understand the additional term, that is AB, where we know the C. But one parameter must be known, either C or pi. If both are unknowns, I don't think so we can able to determine something else. Okay, at least either C has to be given or pi has to be given. Now, is this answers your question?
yes, sir.
Very good. So this completes this sum. Now let us go to another sum. That is in a consolidated drained triaxial test, A specimen of saturated sand failed under an additional axial stress of 250 kilonewton per square meter when the cell pressure was 100 kilonewton per square meter. Draw the Mohr circle for the initial and failure stress conditions. Determine pi dash and the theoretical inclination of the failure plane to the horizontal. What is the shear stress on the failure plane and the maximum shear stress that developed tau max? What is the orientation of the plane of tau max? Compare the maximum obliquity with the obliquity at tau max. Is the factor of safety with respect to shear strength more or less than 1 on the plane of tau max? So this is complete statement of the sum. So first read the sum once and just make me some kind of an understanding what has been given in the sum. So what is your first impression about the Mohr circle if a CD test is conducted on sand?
So the failure plane passes through the origin.
Perfect. So the failure plane passes through the origin. So this should be the first point should come to your mind. So whenever you look at the sum, so especially in shear strength theory, you must understand the sum. Once you understand it, then you will easily get the answer. So either you can use the analytical equations if you remember, else always try to draw the Mohr circle. So which is simplest way, makes your understanding very clear and the thought is also very clear. Okay. So suppose if you read the sum, CD test conducted on the sand, so it is obvious the Mohr column failure envelope must pass through the horizon. That means C dash is 0. C dash is 0. Now, what was asked? Draw the Mohr circle for the initial and the failure stress condition. Now, what would be the possible initial conditions here? What could be the likely initial condition here?
The sigma 1 and sigma 3 would be same.
The simple consolidation of the sample under isotropic condition. Is it true? Consolidated, drained. That means the valve is opened throughout the experiment. So initially you are consolidating the soil sample. So then again under consolidation you are shearing the soil sample. That means the initial condition is that the sample is consolidated under isotropic loading condition. So when I say the isotropic loading condition, your sigma 1 and sigma 3 are equal. Alright. So when sigma 1 and sigma 3 are equal, so how do you draw the Mohr circle?
What is the point?
It's a simple point. Okay. So it is a simple point on the Mohr circle. So this is sigma and this is tau. So this is the initial condition. So initial condition where the sample is, so instead of this one, the sample is consolidated so under a cell pressure of 100 kilopascals uniformly. Or you can say this is nothing but your sigma 1 or sigma 3 until you are achieving the complete consolidation. Now what you have done? By keeping the cell pressure constant, you have increased the deviated stress to 250 kilopascals until the sample is totally sheared. So therefore, your sigma D is 250 kilopascals. Now at failure, what is your sigma 1?
350 kilopascal.
So yeah, 250 deviated stress plus 100 cell pressure. So this is 350. And what about sigma 3?
100 kilopascal.
100 kilopascals. So sigma 3 is remain 100. So this is initial condition. But sigma 1 is so increased to 350. So now I know, so two conditions, sigma 1 and sigma 3. So this is sigma 3 100, sigma 1 350. So the difference between these two will become the radius of the Mohr circle. The radius of the Mohr circle. So sigma 1 and sigma 3. So this is how we can able to draw the Mohr circle. So this is what is the answer to your what are the initial and final stresses. So show with the help of the Mohr circle. That is done. Now determine pi dash. So to determine the pi dash, so you need to come to the initial concern. You need to come to the testing condition, that is CD. It is on a sand. So I know. So the Mohr plane passes through the horizon. Okay. Draw a tangent to the Mohr circle. Draw a tangent to the Mohr circle. And where the C dash is 0, and it makes so an angle of inclination of pi dash. Now whatever the analogy just now we have discussed, follow the same thing. Draw a perpendicular line from the point of tangent to the center of the Mohr circle. So I now know the distance from horizon to the center of the circle, that is sigma 1 plus sigma 3 by 2, and the radius of the Mohr circle, so that is sigma 1 minus sigma 3 by 2. Sigma 1 minus sigma 3 by 2. So I can easily able to calculate the pi value. So what is the pi value? So in fact it is pi dash. So everything in terms of
33.75
33 point.
degree. 75 degree.
Okay. So 33.75. So is this point is clear to everyone? Nishar or Ashwant or Pranav?
Yes, sir.
For everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Now, what is the angle made by the failure plane, that is theta?
$61.875.
So what is the equation?
45 plus 5 by 2.
Okay. So 45 plus 5 by 2. 45 plus 5 by 2. So your theta is 67.
So 61.88 kilonewton. Oh, sorry. 61.88
Per car.
degree.
45 plus 15, 61. Okay. 61 point.
88 degree.
Okay. Approximately 62. Approximately 62. Okay. So where do you indicate your theta f on this Mohr circle? If I ask to indicate this 62 on this Mohr circle, how do you indicate and where do you indicate it?
So we will make the line from sigma 3 to B.
Okay, sigma 3 to B. Okay, sigma 3 to B. So this is called as a theta f or theta. Okay, that is 62. Now, suppose if I ask, what is the angle made by the failure plane at maximum shear stress?
So sir,
45.
45. How do you draw on this Mohr circle?
So at the center, we draw the perpendicular line. So we will get a point that is the maximum shear strength, and we will join the line from sigma 3.
So this is, now this is tau max. Okay, so this is tau max. So this is, say I'm just designating with the alpha. So alpha designates angle made by the failure plane at maximum shear stress. Or any other plane
Can you
is,
repeat? Can you repeat it?
see initially, so I have drawn angle made by the failure plane, that is 62. So that 62 is nothing but a line joining the sigma 3 with the point of tangent. Point of tangent. But suppose if I ask to draw or find it out, what is the angle made by the failure plane at maximum shear stress? So the maximum shear stress is nothing but tau max, which is nothing but the coordinate at the topmost point of the circle, or if you draw a vertical line from the center of the circle, wherever it touches the Mohr circle, that point is tau max. Now, if you draw another line with sigma 3 as the origin and the apex point of the tau max as another point, if you draw this, if you connect these 2 points, then that represents angle made by the failure plane at maximum shear stress condition. At maximum shear stress condition. So that is how we need. So here, you know, alpha is equal to 45 degree. That's it. So maximum shear stress occurs at the failure plane makes an inclination of the 45 degree. So that you can also derive. So there is no problem. Now, what? Yeah.
So from this we can say that means plane it first it pass through 45 degrees, then it is already failed, sir, and it will not reach to 62 degrees, sir.
No, it is it is not like that. So that point I am coming to. Now here suppose if you look at these 2 points, so though the sample is exhibiting the maximum shear strength, that is at tau max, but in reality the sample is failing at some shear strength that is designated as tau ff, which is nothing but the shear strength at failure. So shear strength at failure is different than the maximum shear strength. So the sample always fails at the shear strength at failure, not at the maximum shear strength. So this maximum shear strength is theoretically available. Or other way around, if you are asked to define the factor of safety, you will always define with shear strength upon shear stress. Is that right? Shear strength upon shear stress. Now here, where is the shear strength and where is the shear stress?
Tau max by tau s.
Tau max by tau f. So if you write in terms of the numerals as per this diagram, so this is tau max by tau f. So this value must always be greater than 1. Then only there is no failure that can occur. Suppose if it is less than 1 means the sample has already failed. Okay, so in this case, what is the tau max value? So that is sigma 1 minus sigma 3 by 2. Sigma 1.
125, sir.
So this is 125 kPa. And how do you determine the tau f? So the shear strength at failure,
Sigma 1 minus sigma 3 by 2 sine 2 alpha.
same. Mohr Coulomb failure envelope. So sigma ff into tan pi dash. So since it is passing through horizon, I am not taking the C component. Okay. So now I know the tau max. So if I calculate the tau f, I can able to calculate the factor of safety. But here, so pi dash is known, that is 34 approximately. But how do you determine the sigma ff? So which is nothing but the stress at this location from origin to this point. This is sigma ff. How do you determine the sigma ff?
So we have one formula, na, sir, in normal stress. Sigma 1 plus sigma 3 divided by 2 plus sigma 1 minus sigma 3 divided by 2 cos 2 theta.
Right? Is that equation valid? So again here you need to follow the geometry. You cannot able to use that equation. Or if you use that equation, then again you have to come to sigma ff. Other alternative best is, so take the geometries.
Sir, I use that formula and I get 155 kilopascal, sir.
155 kilopascal. Okay, very good. Any other can confirm?
So
Yes,
from
sir,
that
from
formula,
geometry
sir.
28.
150 kPa.
Sir, I have not used geometry, sir.
That doesn't matter. In fact, that is also derived based on the geometry only.
Yes, sir, it comes out to be same.
Okay, fine. But that cannot be enough. Okay. So sigma ff is equal to 150 kilopascals. So now if this is 150 kilopascal, then what is the value of tau f? So this is 155 multiplied by tan approximately 34. So what is this value?
104.08.
10
4.
104.
0.55.
Okay, no problem. Approximately 104 kilopascal. Okay, now, so just have a small observation. So see, we identified the tau max and we identified the tau f. So as for the geometry, your tau f must be less than the tau max. Tau f must be as per this Mohr circle diagram. So if you are not getting mean, somewhere you are doing some mistake. So this is the first check. Your tau f must be less than the tau max. Okay, since tau f is 104, tau max is 125. So therefore, whatever you are doing is correct. So now we can determine the factor of safety. So factor of safety is equals to 125 divided by 104. No,
So 1.2.
1 point?
2.
1 point. Now there is another question which has been asked. That is called as an angle of obliquity. So the angle of obliquity can be defined as two things. Obliquity. So this is defined as the ratio of tau by sigma. shear stress upon the normal stress. Now, in the sum, what they are asking is, what is the angle of obliquity with respect to the stresses at the failure condition and with respect to the maximum shear stress. So in a sense, you need to determine, so tau ff divided by sigma ff, then tau max divided by sigma max. So you now know all the values, tau ff, sigma ff, tau max and sigma max.
Tan inverse. Angle of obliquity is the tan inverse of.
Huh?
It would be tan inverse tau by sigma, no?
Tan inverse tau by 2.
Tau by sigma, yeah.
Okay, okay, sorry.
So what is mean of this formula, sir? Can you please represent from the graph, sir?
See, so I can draw a line with respect to tau ff and with respect to maximum shear stress. So I know one angle, that is theta 1. I know another angle, so this is theta 2. So corresponding to theta 1, so the sigma ff is different. So corresponding to tau max, so sigma max is different. So this ratio is referred to as the obliquity. Got it now? What is the difference between tau max and sigma max and tau f and sigma f?
Yes, sir.
Yeah. Okay, so go to the next sum. Cu
So one
bar, yeah,
So if CD test is conducted on a clay sample, will the C value be still 0?
CD test conducted on the clay sample.
Hmm.
Just refer to one of our class. If it is normally consolidated clay, then C is 0. If it is over consolidated, then C exists.
Okay, sir. Thank you.
Sir, can you please make the region of y axis have clay 0?
Can you repeat the question?
Sir, for ancestry soil, C equal to 0, sir. Sir, what is the reason for this?
What is the reason for this? Okay. See, first of all, what do you mean by the normally consolidated soil and what do you mean by the over consolidated soil? Suppose if you draw the stress strain curve for the normally consolidated soil, so it continuously increases and reaches a peak. So the rearrangement of the particles happens in such a way that, so there is only the net change, that is only decrease in the volume. But in case of the over consolidated soil, if you look at the fundamental meaning, the soil is already compacted or densified to the maximum state. There is no more possibility of the sample getting compacted. But when you apply the shear stress or the axial stresses, see, unless there is a rearrangement of the particles, the consolidation will not happen. So in normally consolidated, as the sample is in loose state, so there is a continuous decrement in the soil volume. But in over consolidated, the sample is already compacted to the full extent. No more positive volume change is possible. Rather, expansion is possible. Okay. So just imagine what is happening to the resistance when you apply the stresses to these soils. So in case of the normally consolidated soils, as the particles are arranging, so they will overcome the cohesion component and only the particles are arranged such that it offers maximum internal friction. But in case of the over consolidated soil, the densified state already encompasses both the C component and Y component. because you are no more arranging the particle, rather you are disturbing the arrangement of the particles. That's why the C component and pi component exist.
So that means we can say normal ancestral soil have negligible C value. It is not equal to zero, na, sir.
In which case?
So NCC.
No, it is zero, na?
Means all means due to particle rearrangement only they are means
See, when the particles are rearranged, okay, so they will try to overcome the cohesion component. Okay, so when they are arranging, the interlocking phenomena comes or makes a more dominance than a mere cohesion component. So unless you overcome unless you supersede that cohesion component, so the frictional component will not come into the picture.
okay, sir.
Okay, another way of understanding this one is, see, what you do in consolidation drain test, so you allow the water to expel out. Okay, when the sample is fully saturated, so it is obvious that so the cohesion component is to the maximum possible minimum. Okay, and when water is coming out from the soil sample, so the arrangement happens at the particle contact level. So no attraction or something comes into the picture. Hey, let's refer to some books.
Thank you, sir.
Yeah. Just go through some books, you will understand in much better way what I do.
Sir, in exam these types of problem will ask.
Yeah.
So there will be theoretical question also.
Yeah, theoretical as well as problematic, both. See, look at the next sum. CU bar test, CU bar triaxial test conducted on specimens of a saturated clay soil gave the following results. Cell pressure sigma 3. So initially 150 kilopascal, then increased to 300, then to 450, then to 600. Then corresponding to cell pressure of 150, deviated stress of 102. Then the recorded pore water pressure is 80. So full list has been given. So you are asked to determine the effective stress path parameters C dash and pi dash by the Mohr circle method and the stress point method. So here Mohr circle means now I know sigma 3 value, I know the deviated stress value, I know the pore water pressure. So therefore, so it is quite easy for you. You can able to calculate sigma 1, sigma 3, so sigma 1 dash and sigma 3 dash. Because everything is known. Straight away calculate everything. So draw the Mohr circle, that is normal stress versus shear stress. So that is normal stress versus shear stress, and try to find it out your C and pi values. So C and pi value. Now in another step, you are asked to calculate by the stress point method. So when you go for stress point method, what is that relationship? What is x-axis and what is y-axis?
Sir, Y is Q and X is P.
Okay, so P R P dash, Q R Q dash. So how do you define the P?
So sigma 1 plus sigma 3 divided by 2.
Sigma 1 plus sigma 3 by 2, and Q is sigma 1 minus
Sigma 1 minus
sigma
sigma 3
3.
divided by 2.
But here one important thing now I must tell you. Uh, how much time we have? So here it is straightforward. You will get a curve of something like this. So you have 4 points. 1, 2, 3, 4. So 1, 2, 3, 4 points. But so if you look at carefully, this is pi dash or pi, while the angle made by the failure plane in respect of P versus Q is xi. So I told, how do you relate these two? So this relationship can be expressed as sine pi is equals to tan xi. Tan xi. And again, so when you draw the P versus Q relationship, you will not directly get the C component. So this is cohesion. Rather, what you get is subordinate, that is A. So how do you relate the A with the C? So C is equals to A by cos xi. A by cos xi or A by, yeah. So A by cos phi. A by cos phi. Okay. So try to practice yourself. First draw the Mohr circle. That is the relationship between normal stress versus shear stress. So draw the Mohr Coulomb failure envelope. So by drawing a line which is tangent to all 4 Mohr circles, then try to determine the ordinate, that is cohesion component, and angle made by this Mohr Coulomb failure envelope, that is angle of internal friction. So in the next step, keep on calculating the P or P dash and Q or Q dash. So and draw a line. So this is called as a KF line. So this is called as a KF line. So this is not a Mohr Coulomb line. If you draw the failure envelope in terms of the P versus Q, that is called as a KF line. So where K is defined as the horizontal stress divided by the vertical stress. Horizontal stress divided by the vertical stress.
Sir, in question it is asked to determine by analytical method. So we have to draw the Mohr circle.
Yeah, to the Mohr circle.
Sir, we have another class.
No, it's not analytical. Determine the effective stress strength parameter C dash and phi dash by the Mohr circle method and stress point method. Not analytical. You need to draw the diagrams.
Sir, we have reached class.
Okay. You can sign off now.
Is there a way that you can shift the Saturday shift